But this guy here is just reflexivity, right? So this guy holds for every element. This is reflexivity of judgmental equality. So they play nicely with each other, okay? And now, because I made such a nice derivation of this rule, right? Now you believe me that here I could just say, actually, I can rewrite this type to x equals x, because this is judgmental equal to x, and then I can just do REFL x. And it's basically this rule I could just compute away. So yes, okay, I'm cheating, it's not this rule, it's the symmetric version of this rule, but you can just use symmetry everywhere and you're done. Yes?
Actually, what I was going to ask and what I waited, so are you saying because of the congruence rule, you could literally that would be inhabited not by J lambda REFL, it would just be REFL? Because when I implement this by hand in Anja, or it is the only constructor is REFL, and I don't see mention of J, and I definitely don't see it wrapped. So I guess my question is,
where's J in Anja? That's your question.
Yeah.
Yes, that's an excellent question. They're hiding it from you.
Okay.
So what you do, right? And that's when that's why I say, something is wrong with the properties, and then you know what it is, because half of it is hidden. So yeah, it has to be J in this case, because X and Y are not necessarily the same, whatever, right? But what you do in Anja, right? You'll try to prove this, and then you will press something like Control-C, Control something L, and it will create a hole, and it will say now you just need to do the REFL thing, right? And this, you're pressing the stuff, right? It's actually going to reduce your goal to, just give me an element of this, and it will only say REFL, right? So the J is you pressing these buttons, and then like the system itself will actually say, I will use the induction rule, the elimination, here the J rule is called the induction rule for the propositional equality, or the elimination rule, or J rule, whatever. And when you type it up, it'll say, just do it by induction, right? And because the induction rule says all you need to provide me with is this, the system will then know it was provided the entire function, right? So that's why it looks like it's just REFL, but it's not just REFL, it's the induction principle plus REFL. It's just you never got to see the induction principle written in syntax. Yes?
Sort of basic, might be an ill formed question, but what's a good way to understand what J is doing? Like, is J taking you from a proof that X is equal to X to a proof that a property holds for what is the same as X?
So I think of J as a way to define functions out of the equality. So how do I define a function on the equality type, right? If in the domain is the equality type. This is how I think of it, right? And it's basically telling you, if I want to define a function that, kind of depends on the equality type, right? And, I didn't answer the question, how do we know what it is if not true? Right? Well, it's hard to say because all you have to do explicitly is prove it for REFL, right? This is what J is doing. It's eliminating out of the equality type. So that's all I got. This is my intuition, and it's also the definition. Yes?
Maybe what helped me when I first had problems with this is that for all other elimination principles, we always just have to tell the function what it looks like on canonical elements. So for the dependent sum type, for example, we only have to tell it what do we do if we actually have a pair, not if we have an arbitrary element of the sum type that might look different, variable.
It could be a variable, it could be something that we know is going to be this type, but it's a variable with some.
And here we have the fortunate position that the canonical elements are pretty easy for us to understand. It's only reflexivity. And so we only have to do reflexivity because that's the only canonical elements we have, and then the function magic does the rest. That's how I see it.
Okay. And this is a very good analogy. Right? Before we had the natural numbers, right? And the canonical elements of the natural numbers were 0 and the successor. So we had to define it just for the 0 and the successor, and then if you have a variable that is a natural number, right? We will kind of know it will be composed of these guys somehow, right? Like intuitively. But we only had to define it by induction on 0 and the successor. And here, like our colleague said, it's only, the only constructor is the reflexivity. So if we define it on reflexivity, magic does the rest, and the magic is called the J rule. Yeah. Okay, one more good point. So I commented on how this J rule looks in Agda. It looks like you pressing the button to say induction. In ROP, and I think also in Lean, it's basically just using the tactic called induction, right? So you say induction on the element of the propositional equality type, and it will reduce your goal to then just prove it for the reflexivity case. All right. So we did formation, interaction, intermission, constellation, congruence rules. I had a nice explanation of actually judgmental equality. So, right, one more thing I wanted to say. Here, it kind of looks like the judgmental equality is the thing that is computing stuff in your propositional equality. Right? And this is basically how most proof assistants I know use computation, use judgmental equality. Right? This is the stuff that is under the hood that you don't see, because the kernel of the proof assistant will compute with these judgmental equalities, and it will hide it away from you so you don't have to, right? All of this thing that I've been telling you yesterday and the things that I'll be telling you today is the stuff that the proof assistant does automatically, right? And that's so when it gets stuck and you don't know why, right? It's probably because some of these rules had a problem, right? And now you at least know what these rules are in principle, right? And these derivations, like this, you don't want to do them by hand, and the proof assistants allow you that you don't have to. Okay. A few more things I want to say about the propositional equality. So we saw that the judgmental equality is a nice equivalence relation, and also the propositional equality should be a nice equivalence relation. Just a sec. So we already see that it's reflexive by definition, but it's also symmetric and transitive, and that's what I want to talk next after I answer the question.
It seems like this definition only allows us to talk about things being equal when they have the same type. Is there like a way around this?
That is a good question. So in Markov type theory, the way I define it, no, we don't have it's called polymorphic. Okay, yeah, heterogeneous. Yeah, sorry. Yes. So we could have a type theory that has heterogeneous equality, but not in this setting. So no, here I'm strictly demanding that we can only say that, we can only talk about propositional equality when they have the same type. Why would you want heterogeneous equality? So you wouldn't really want to talk about things being equal when the type is not in principle equal. It's maybe just not, syntactically equal or something, right? So for example, here we have a type that is x equals at x0, right? But morally, it's equal to x equals x, right? And this time it's just, it's even syntactically, in a sense, equal because this is the judgmental equality that computes it away. If I had it the other way around, you would also morally want to think of it as x equals x, right? But then, if you want to have terms that have like type this, and you want to talk about equality between them, if it's judgmentally equal, you can just convert, use the element conversion rule to talk about equality at exactly the same type. If it's not judgmentally equal, then it's a bit of a problem. So in Markov type theory, no, you can only talk about actually having the same type. But as I said, the mental equality and the element conversion rule is a bit, it's stronger than that, right? So you can always convert the type to the one that you want if it is mental equal, and then you can talk about it, like somewhat heterogeneous equality. Okay. Symmetry and transitivity are the next two. Let's try with the transitivity first. And I want to keep these rules here. Maybe this one. Ooh. I discovered treasures. Something about finite types and such and da-da-da. Have you been reading the textbook ahead? That's what happens when you have really good students. They already know the material. Okay. Transitivity, okay? What I want to say about transitivity is that I have a function concat that, concatenates two paths. So if I say a path, I mean an element of the proof, an element of the propositional equality type. Because, the propositional equality type, so people, the mathematicians, they like to have these nice analogies, right? And in the homotopy type theory, people think of the propositional equality type or the identity type as the type of identifications, and for them, identifications are like paths between one element to the other, right? So that's why they think of transitivity as concatenating one path with, if I have x, y, and z, and I have a path here that identifies x and y, and I have a path here that identifies y and z, then identification between y and z is like the concatenation of these two paths. Okay? So this says that if I have some type A, and I have x, y, and z of type A, then if x is equal to y in A, and if y is equal to z in A, then x is equal to z in A. Okay? So again, let's try to use the J rule, because obviously it's sort of a function out of the identity type, right? Out of the propositional equality. Okay? So if I want to construct this concat, so I want to say concat is defined equals as something, what would it be? Well, I already told you I want to have J, but if I look at how J looks like, right, it's giving me a function of this shape, right? And it has to be first A, then B, then equality between A and B, and then my type family, right? And here I have something slightly different. I have x, y, and then I don't have immediately equality between x and y, but I have z first bound, and then I have the rest of it. So what I want to do instead is I don't want to define concat immediately. I'm going to define a function called g that just permutes the arguments a little bit. So I'm binding x and y in A first. So this is just a shorthand for two pi's, right? So to be pi, it's like pi x, pi y, pi z. I just use one pi so there's no guy trying to write this. And then I'm giving myself x equals A, and then I'm giving myself pi z, and it's nice because z is not mentioned in this type anyway, so I can do this. And then I'm giving myself the rest of them. Y equals z, and then x equals z at A. And I'm going to say concat is actually equal to, so concat at x, y, z, p, q, t R, what's the next one, R? The alphabet is actually equal to the function g at x, y, p, z, q, r, right? So I permuted the z and the z and the p arguments so that I can use the j rule directly. Right? And now I want to define g as j of something. Okay? So now I look at this j, and I need to figure out what my p is, right? So p will be whatever comes after the first two elements in the first equation. So my p, big P, okay, will be pi zj, y equals z, to x equals z. Okay. So this is my p, okay? And g will now be the j part. And now that I know what my p is, I need to give it the diagonal, right? And I need to give it something lambda x, right? So, and here I need something of type p x x rep x. So, what am I looking at now? I probably, okay, so here I have p of x and y and p. So this has to be something of form, I will write the full thing. I need something pi lambda x, and then I need, okay. I know that p has to be of this form, and now I want to do the diagonal, so x and y have to be the same guy and the reflexivity, right? So I need something of type pi za, x equals z at type A, and then I'm giving myself x equals z at type A, right? I need this. And this is very easy. It's lambda z, the identity function on the type x equals z at type A. Okay? So g is j applied to lambda z, identity at x equals z at type A. Yes, no, maybe. It's in the notes. Exactly.
Sorry.
Yes.
Is the R, I think Concat has one too many arguments. Is that
That's probably true, yeah.
Okay, thank you.
Thank you. Yeah, just, inserted the argument for the last thing that is actually the type that I have to land in.
Yeah.
Yes?
We also need lambda x in front of the lambda z as the argument of j, right?
Yes. You are absolutely correct, because here I have to first bind x, and then I have to give p at x, x, referral x, right? And the p itself is binding z, so I needed to have lambda x, lambda z, and then this thing. Very good. You're all listening to me. Yay! Okay. Now this is hard. Okay? Even I needed to make 3 mistakes at least, and the rest you will tell me. What we morally want to do is what you do in Agda when you click and then just give it REPL, and in Rock where you just click, you write reduction, and then it reduces stuff, right? So how we usually use the J rule is just pretend that we have the reflexivity case here, okay? So what you would morally do, and what you usually do, you would just say, purple, you would say that to build a concat operation, it suffices to show the case where x and y are equal, okay? So you would say it suffices to show that I have a function from x to z, x is equal to z, x is equal to z. Okay, right? Your proof assistant, right, assists you, you say, I want to define this by induction on the first, well, 1, 2, 3, blah, 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 this argument, fourth argument, first, second, third, fourth argument, and then it would just give you, oh, well, if you want to do that, just give me an element of this type. And then you would say, no problem, it's the identity function. Done, right? This is the amount of information that you want to be required to provide, right? You would say induction, and then it would ask you, give me something of this type, and then look at the type, and you say, easy. It's the identity, and I didn't even say which type, right? You just add the identity function. And then because the proof assistants are so smart, we use them, right, by not really understanding what we're doing. So I am fully guilty of seeing a complicated Smith statement to prove. Then I try all tactics possible. I have to keep induction at some point. Does the magic, asks me for this, and I say, oh, I know how to do this, right? Or I forget, and I say, oh, obviously induction, because this is a, we call it that, induction again or something. And then, I try, maybe in this case induction won't even work. So we will do it, right? Until we come to the place where, we can't think of a natural term to do, and then we start thinking, right? So part of this, moral of this story is, it's okay to be lazy and to just be required to do this. But the other part is that when you get stuck, sometimes it's not the proof assistant. Sometimes you didn't really understand what you were doing when you were typing stuff up. So knowing what the J rule and the induction principles in general are about maybe helps you to maybe generalize your lemmas, or to know what is going on behind the scenes when you're typing your tactics, or just importing induction principles with random key bindings that add them once in your proof assistant.
So to make sure I understand a few things, the first thing is concats. If you give concats a proof that x is y, then concat will be able to turn proofs that y is z into proofs that x is z.
Yes.
Okay, and the second question is, I think I got a little lost in what the p is there. Because if I...
P here?
Yes, like, should I think of it as like sort of a fun, I know it's a type that depends, or family of types.
So P, this P, I was just trying to say that if I want to use the J rule, I would use it with P in the premise that is concretely this type, right? I'm using it in a specific case where P is this type, this dependent type.
I think maybe my confusion is if P has like an array of 3,
Yes?
and that pi only has one argument, which is the z.
Yes. P, okay. P here is applied to x, y, and z.
Okay.
But you can see it because I scribbled it and it's ugly. This pi z is already a part of this right-hand side of the turnstile. Okay? It's not x, y, and p. Right? Z is already here. Right? The pi z comes on this side. Yeah. That's an important one. Okay. Question?
So with the p there, so p with some arguments, that's an equals pi of something, or?
Yes. Okay. I screw up. So yes. See, it's pi me yes. P of x, y, z is equal. Okay, I will use the squiggly equals, so it's not the judgmental equality or the propositional equality, but it's our meta equality that we're mentally plugging for this P, this type, high Z, X, Y equals Z, X equals Z. Yeah? Question?
Why do we now have V twice? It shouldn't be
Ah,
P
so
then.
it was P, little p. It was always little p. Little p from the proof that X equals Y. Yes. More questions? Was that the same question back there? Yeah. Okay. So it's transitive. It's also symmetric. So we have the inverse operation. Okay. So let me just write it here. Is this still visible, this part here, or is it too low? So we have inverse operation that says phi x, y, and a. If x equals y propositionally, then y equals x also propositionally. Okay? Now let's do the lazy thing, not with a j, right? I want to say what I have to do just for the diagonal case, right? So if I look at the j again, the diagonal case says, what happens if I have, give me an element of phi x in A, x equals x, to, oh, wait, what am I doing? I just have to give you this guy, so the diagonal will not ask me for this. The diagonal will ask me just if x and y are equal, give me an element of x equals x. Okay? So what I can say, inverse of raffle x equals raffle x. Okay?
And this is propositional equality, right?
This is judgmental equality, thank you. Or even better, it's colon equals. And that's the definition, and then we insert two rules that I showed you yesterday into the type theory to make this definition. Okay. And it's, informal way of using the J rule. It's enough to say what happens if this is raffle here, right? That means x and y are syntactically the same thing. X and y, if they're syntactically the same thing, then I know that I can put raffle in, and that's it. Okay? That's the magic. Yes?
So couldn't we have done the same informal thing over here and said raffle composed with raffle is raffle? Instead of using J, I guess it's an informal use of J.
Yeah, I just wanted to show you how formal to use J.
Yeah.
Yes. I mean, what I will do here is concat of x raffle is equal to the identity function on x equals z. Yeah?
What's the question about the piece in general? I should not be thinking of these as functions. I should be thinking of them as types that depend on what is in the parentheses, and not as functions.
So they are type families, right?
Okay.
The first lecture, I was all about dependent types, and this is a type family, right? This is a type that depends on whatever is in the parentheses. All right. We can do other nice things with the propositional equality. So there are two more things that I wanted to show you. One is the action on paths, and the other one was the transport that was a question, right? So the action on paths, so morally what we want to do, right? If I have, yeah, I need more space. And I don't want to erase the J rule, but I will erase the computation rule, right? Because you morally know what the computation rule should be. If I have an equality between A and B, the propositional one, then what I want to say is that if I have a function on these, applying the function is also the same, right? So if I want to say morally that if A equals B at type A, and I have a function from A to B, then f of A is equal at type B to f of B. Okay? I want to kind of apply the function to both sides of the propositional equality, and I want it to give you the same thing. And this is, we call it action on paths. I will use AP with index f because f is going from A to B. And it basically says for every x and y in A, if x is equal to y, then f of x is equal to f of y. Right? And this one is happening in A, and this one is happening in B. And how we define it? Well, we say it's enough to define AP on REFL. So what happens at x, REFL at x, right? And it's going to be whenever this is REFL. So if I say x and y are syntactically equal, I need to provide something of the type f of x is equal to f of x, which is REFL f of x. Perfect. REFL f of x. So this is the action on paths. And we also have the transport, which is a similar kind of thing. It's just that we want to have a dependent type family, right? So if I have B, a type family over A, then I have a transport of this type family, which is if I have x and y in A, and x is equal to y at A, and then I want to say I can transport proofs at x proofs at y, right? So, this is a type family over the type A, and in the like if I have a section of x, then I want to know what it corresponds to at y. Right? And again, we can define this transport at B, and it's again a REFL case. Right? And if I take, okay, what type is this?